Hello, in this video, we will be providing a description of our Aspen model, our simulation decisions, the energy analysis, and show that our Aspen simulation converges. We will first start with the thermodynamic model. We have selected a global model of SRK equation of state model. This is because an equation of state model such as SRK is suitable for simulations with high pressures and temperatures. On top of that, the SRK model handles systems with polar molecules well. These molecules exist in high abundance throughout a process. Finally, the SRK model uses the NBS stream table to calculate steam properties. This gives us a better accuracy.
The first step in our process involves desulfurization. Here, hydrogen sulfide is adsorbed on a solid zinc oxide bed in a fixed bed reactor. This produces zinc sulfide and H2O, removing hydrogen sulfide. Aspen does not provide the capability to model this, so a standard separator was used to mimic this unit in the process. For the separation, a Radfrac model was chosen. This was due to its rigorous nature and high degree of accuracy, especially when it came to components with narrow differences in boiling points, like we have. Thus, it was better suited than the alternative DSTWU model. For the separation, the unit was operating at minus 107 degrees Celsius and 15 bar. This is so that methane enters the column in a vapor phase, whilst the remaining hydrocarbons in a liquid phase. These were vital for our separation. The column has 10 stages, with the feed entering at stage 6 and a reflux ratio of 2. These were found to be optimal values to obtain the desired separation.
The piriformer operates at 450 degrees Celsius and 35 bar. By using elimination, R-stoic was the final model used to simulate the piriformer since we have the stoichiometry and extent of reaction. R-plug was not used because we do not have the kinetics of the reaction that occurs in the piriformer. Also, R-equilibrium and R-Gibbs were not suitable as the reaction is not in equilibrium.
The autothermal reformer, where most of the hydrogen is produced, requires the supply of oxygen. This is supplied from an air separation unit that utilizes cryogenic distillation. The air is compressed to 6 bars and cooled to minus 173 degrees Celsius before entering the distillation column. A DSTWU model was used for this separation as there were 3 nonpolar components which undergo a simple separation using 45 stages and achieve the required purities closely matching results found in literature research. Methane and steam from the pre-reformer mixes with this oxygen and are heated to 1000 degrees Celsius and compressed to 35 bars before entering the ATR. As multiple reactions, both exo and endothermic, take place in the reactor, as shown below, a Gibbs reactor is used as it considers the reaction kinetics between all the components present. By comparing the product stream compositions with those found in literature research, we found them to be very similar, confirming that the Gibbs reactor modeled these reactions accurately.
The product from the ATR will then enter the shift reactors. This consists of a high temperature and low temperature reactor, each operating at 400 degrees Celsius and 210 degrees Celsius with a pressure of 1 bar. The following reaction occurs to remove carbon monoxide from the system, producing more hydrogen. This reaction is made possible by using the following catalyst in each reactor. An R-stoic was used to model this reactor. This is because the reaction is highly dependent on the reaction kinetics. Hence, R-Gibbs and R-equil is not a suitable model. However, the model could be improved if the kinetics were known for the specific catalyst.
Most of the CO2 purification occurs in the absorber, which uses MDA as the absorbing solvent. Prior to entering the column, the product from the LTS is compressed and cooled to the absorber's optimum operating conditions of 16 bar and 120 degrees, as found in literature. A Radfrac model was used for the absorber because it can simulate an absorption process with an ongoing chemical reaction, and it can also have multiple feed streams, which is required to feed in the CO2 and the MDEA. The top stream from the absorber is passed into a flash operating at 40 degrees and 10 bar to separate the unabsorbed CO2 from the remaining components being fed into the methanator. The bottom stream from the absorber is fed into the stripper at 10 bar. A Radfrac model has been used for the stripper for the same reasons as the absorber, in order to separate CO2 and recover MDA, which is recycled back into the absorber. The top stream from the stripper is then fed into flash 2, operating at 110 degrees and 12 bar to further purify CO2 to match the desired specification.
As for the methanator, it operates at 250 degrees Celsius and 30 bar. Since the two reactions occur in the methanator are in equilibrium, R equilibrium and R Gibbs were considered to simulate this unit. R equilibrium requires to estimate the extent of these reactions where we assumed 100% conversion in the appraised stage, whereas R Gibbs does not require this information, therefore R Gibbs was chosen as the final model.
For the ammonia loop, all the streams that go into it are pressurized to 200 bar, then heated up in stream 52 to 450 degrees Celsius. This temperature and pressure are chosen to get a conversion of 40% as the reaction reaches an equilibrium. In the reactor, 3 moles of hydrogen react with 1 mole of nitrogen to give 2 moles of ammonia. Our stock is the model chosen to simulate the reactor, as the stoichiometry, the molar extent and conversion are known. Then pressure drops to 24 bar thanks to a bath and enters in a flash. As the boiling point of ammonia is higher than the rest of the components, it condenses and is separated in this flash, reaching the purity needed. The reactants that have not reacted are recirculated to the reactor, passing before through a compressor to have the required pressure of 200 bar again. A patch is needed because otherwise the inerts would accumulate within the loop. Since they represent a little part of the total flow rate in all the streams, for non-Western reactants, the split fraction is 10%.
This figure shows the units involved in our process along with their heat duties. The hotspots are highlighted with the ATR requiring the most heating and the ammonia reactor requiring the most cooling. To create heat savings, a heat exchanger network was considered. The 6 most energy consuming streams were taken in for a pinch analysis. We conducted the pinch analysis in an attempt to integrate these streams to reduce the heat duties required. As you can see, the following matches were found. In total, the 6 streams had a 62% reduction in heat duty, saving close to 370,000 kilowatts of heat duty requirement. Using Aspen, we can show how these streams will be integrated in our process.
Finally, we'll be looking at the convergence of our Aspen simulation. From running the Aspen file, you can see it has produced results with no warnings or errors.